In this lecture video, we are going to talk about PEM fuel cells operating conditions. Whenever we are considering a PEM fuel cells, we are interested in the output power that can be delivered by the cell. This output power is of course connected to the output voltage of the cell and the current we can draw out of the cell. The output cell voltage can be evaluated using the following equation. In that equation, the first term, E, gives the electromotive force or reversible open circuit voltage, OCV, of the hydrogen fuel cells. It can be evaluated using the Nernst equation. In that equation, E0 represents the output voltage of the cell at standard condition. It can be calculated knowing the change in the free energy occurring during the reaction of oxidation and reduction of hydrogen and oxygen, giving water. Of course, when the PEM fuel cells run, we are not at standard condition, so the pressure and temperature might differ. Therefore, we have the second term. In that second term appears R, which is the gas constant, and F, the Faraday constant, N, which is the number of electrons involved in the reaction, 2 in the case of the hydrogen electrode, and the temperature. In the logarithmic term appears the partial pressure of the gases, so hydrogen, oxygen, and water vapor. The second term we are talking about here is actually a loss. And this loss, this activation loss, can be evaluated using the Tafel equation. In the Tafel equation appear the term A, the constant A, which relates to the charge transfer coefficient. The charge transfer coefficient signifies that the reaction, or a fraction of the interfacial potential at the electrode-electrolyte interface, that helps in lowering the energy barrier for the electrochemical reaction. The activation losses are caused by the slowness of the reactions taking place on the surface of the electrodes. So a proportion of the voltage generated is lost in driving the chemical reaction that transfers the electrons to or from the electrode. This voltage drop is highly nonlinear. You have also a second term appearing here, that is I0, the exchange current density. The exchange current density is higher if the reaction is faster. The current density I0 can be considered as the current density at which the overvoltage begins to move from zero. This current density I0 is usually called the exchange current density because the reaction is taking place at all the time. But the reverse reaction is also taking place at the same rate. When we are running a fuel cell, drawing a current, we are simply shifting in one particular direction something already going on, rather than starting something new. So here is a plot of the Tafel equation. And you can see two curves with two different slopes. So on the left axis you have the losses due to this activation losses. The red curve is for a slow reaction, and you can see that comparing with the green curve, the overpotential or losses are greater for lower current density. If we now fit the straight part of the curve with straight line, the intercept we find will define I0, the exchange current density. If we want to reduce the activation over voltage, we can play on A and I0. And we now know that the exchange current density I0 is the crucial factor in reducing the activation loss. A crucial factor in improving fuel cell performance is therefore to increase the value of I0, especially at the cathode. This can be done in the following ways. Raising the cell temperature, using more effective catalysts, or increasing the roughness of the electrodes. Indeed, this increases the real surface area of each nominal square centimeter, and this increases I0. We can also increase the reactant concentration, for example, using pure oxygen instead of air, or we can increase the pressure. This works because the catalyst sites are more effectively occupied by the reactants. And now we're going to talk on the third term in the output cell voltage equation. This third term relates to the concentration losses. And in the equation to evaluate these losses, you can see the term IL. IL is actually the limiting current density. IL is the maximum current at the maximum supply rate of the fuels. If we want to decrease these concentration losses, then we have to improve the gas diffusion up to the electrode. So we have to work on the gas diffusion layer and electrode design, but we can also increase the gas pressure or gas flow, and we can also increase the temperature at which the cell is running. By increasing the temperature at which the cell is running, you actually favorize the diffusion of the gas within the gas diffusion layer and within the electrodes. The last term on the output cell voltage equation is the ohmic losses. So the ohmic losses obey, of course, the Ohm law. And the resistivity we are talking about here can be splitted in two terms. One term belongs to the membrane and the other term belongs to the electrodes. How to reduce these ohmic losses? Well, the use of electrodes with the highest possible conductivity is of course welcome. Good design and use of appropriate materials for the bipolar plates or the cell interconnects is also crucial. Another way is to make the electrolyte as thin as possible. However, this is often difficult, as the electrolytes sometimes need to be fairly thick, as it is the support onto which the electrodes are built, or it needs to be wide enough to allow a circulating flow of electrolyte. In any case, it must certainly be thick enough to prevent any shorting of one electrode to another through the electrolyte, which implies a certain level of physical robustness. To summarize, if you want to decrease the ohmic losses, you will need good design for the electrodes and for the membrane. But there is one more parameter you have to take into account. The membrane might get dry when the fuel cell is running. Therefore, you need to provide some water in the gas feeds in order to prevent that drying. And now I will show you how these losses show up in the polarization curve of the fuel cell. The green line here represents the open circuit voltage of the cell. It can be calculated, as we've seen previously, using the Nernst equation. But before going to the losses that were presented, I have to add one more loss. This loss is due to the crossover. It's here represented by the blue tick. The fuel crossover or internal current losses results from the waste of fuel passing through the electrolyte and to a lesser extent from electron conduction through the electrolyte. The electrolyte should only transport ions through the cell. However, a certain amount of fuel diffusion and electron flow will always be possible. This crossover loss is negligible when you compare to the other losses that we spoke about. And the first one is this activation loss. You can see that it's highly nonlinear with the current increase. The main contribution comes from the cathode side. Then comes the ohmic drop, which is linear with the increase of the current. And here we have contribution from the cathode, from the membrane, and from the anode. And finally comes the concentration loss that we talk about. So what about the operating condition? Well, we can choose actually favorable condition to limit all these losses. And as we've seen, we can play on the pressure and the flow of the gases, we can play on the temperature, and we can play on the relative humidity. So the pressure, the flow, and temperature parameters should decrease the activation, the concentration, and the Ohm losses, while the relative humidity should decrease the Ohm losses only. So how this results on the polarization curve? So here on this graph, I have added the power. If now I plot it for two different temperatures, so a fuel cell has been run at two different temperatures with an increase of 60 degrees for the highest temperature. And you can see actually a gain of about 9% in the power delivered by the fuel cells. Here, by increasing the temperature, we increase the catalytic activity, we decrease the cell resistivity, and we increase I0. We can also play with the pressure. And here, a fuel cell has been run at 1 or 3 bar. And at the highest pressure, a gain of 10% in the power output of the fuel cells was reached. Again here, playing with the pressure, we can increase the catalytic activity and we can increase I0. Then we can play on the gas composition, whether we use air or pure oxygen. So this is here again a curve taken at the same pressure of air or pure oxygen, and you can see gain when using pure oxygen instead of air. Finally, I will leave you with this table displaying the parameters for the operating condition of different types of PEM fuel cells running with different fuel: pure hydrogen, hydrogen from reformer, or methanol.